taking a look at using Kirchhoff's laws to solve circuit problems. To start with, we're taking a look at this page from your packet on circuits. At the top here, it says solving circuit problems using Kirchhoff's laws. I'm going to take a copy that I've made of this that's a little bigger so I can show you something new here. This document, so far, I just want to kind of add a little something in here. So let's go to my larger version of that part. But first, let's talk about what Kirchhoff's laws are. So Kirchhoff has these two laws of circuits. The first one is called the junction law. And that law goes like this. Imagine, if you would, let's say we have some wires here, right? And maybe some wires come in, all coming into this spot here where they're all meeting up. A spot where wires meet up, where things link up, that's called a junction, okay? And let's say that we have some currents flowing in the circuit like this. We may have some current flowing in this wire. We're going to say that that's I1. And maybe there's some current flowing this way in this wire. We'll call that I2. Current flowing like this, I3, I4, and I5. All right, so there's my currents. And that's showing you the directions that are actually flowing in the wires. So if I want to look at this and I want to talk about how these 5 currents are related to each other, like write a little equation saying, oh, these currents equals these currents, what equation could you write? Well, if you think about it for a while, I think you'll come to the conclusion that I1 plus I5 must be equal to I2 plus I3 plus I4. How did we come up with that? Well, we said we have these charges flowing down the wire, and the current is how much charge per second is flowing in that bit of wire. And you say, well, however much is flowing here, I1 and I5, what makes those guys go together? And I2, I3, I4 go together. Why do we group them this way? We said I1 and I5, those are the currents that are flowing towards the junction, into the junction. In I2, I3, and I4, those are the currents, that's where the current is leaving the junction, going out from the junction. And isn't it true that however many charges flow into this point each second, that many charges have to flow out, or else they'd be like building up in there, right? Or be creating or destroying charges. And you can't create or destroy charges. This is really just a consequence of the law of conservation of charge. And so I can write this a general case instead of just I2, I3, I4, I5. A special general way of writing this is saying if I add up all of the currents going into the junction, they had better equal to all of the currents added up that are leaving the junction, going out of the junction. So add up all my currents going in towards the junction minus all my currents going out away from the junction. Okay, and that's the way we're going to do it. So I can write equations like this, right, using the junction law. Okay, and I'm going to use those equations to help me solve some of these circuit problems. Kirchhoff's other law is called the loop law. Okay, Kirchhoff's loop law. And this one, it turns out, is just another consequence of the law of conservation of energy. Let's put this one like this. Let's say that we have some great big positive charge here, say some great big plus Q, all right? And you say it's going to make an E field that radiates outward from it, right, in all directions, right? Let's say that we go ahead and we take a look at one location here. We can call it location A if we want, but whatever, from this one location, and say that I wanted to calculate my delta V. And I'm going to calculate my delta V using that path integral equation. It's one way of thinking about it. Delta V is negative integral E dot dr. And so, for example, if I went along a path from here to here, going this way. You say, as I'd move, I'd be going along the E field line, right? Electric field lines radiate out from this guy. I'd be going with the field. And so when I do the dot product of my path, dr here, going along the path radially outward, right? You say the dot there would be in this case, I would get a cosine of 0 degrees, which would make this positive 1, where it'd be a cosine of 180. Cosine of 0 is positive 1. And so I just have the E field strength times the distance I go, right? And I'd add that up from each little dr, distance is going along, right? And I get some value. The negative sign says actually it's going to end up being negative, right? Because this cosine of 0 is going to be positive here, but the negative in the formula makes it negative, which makes sense because as I go farther away from the positive charge, I'm going to lower potential, lower V value, right? And so I need my delta V to be negative as I go away. And that makes sense. That's why that formula works. But here's where the loop law comes in. By loop, what I mean is if I apply this formula to a path, right, that I'm following, and I make this path a complete loop, then you say I would go along, and maybe here I'm going with the field. Here, look, let's make a path like this. What if I go dot, 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 dot? Do you see I'm trying to keep the same distance away? Well, now, if I think about the E field that this thing creates, right, that electric field radiating outward, right? Now I'm going perpendicular to the E field. I'm actually going along an equipotential line, aren't I? Right? And so my V value wouldn't be changing. If I did the dot product here, my path going perpendicular to the E field lines, right? Yeah. I would have a cosine of 90, which would give me 0. And I would have, so then you say, well, gosh, that means there's no delta V. It makes sense. It's an equipotential line. I'm not pushing with or against the E field if I move my hypothetical positive charge along here. And so you say, so we're not changing the V value at all. But then what if I went like this, and went back in like that, right? Now I'm going, my path is going this way, right? I was going out this way, and I'm going this way. Now I'm going against the E field. It'd be a cosine of 180 here. And so you say it'd be E times negative 1. So I'd have this negative, right? Which then, as I'm going against the E field, and you say, but then when I add up all those bits, then I've got a negative sign here in the formula, which is going to make it positive. I'm going up potential as I head towards the positive. That makes sense. And then I could go ahead, I could finish this up like this, along that's meant to be at a constant distance out, right? Path along, right? And you say along this one, I'd be going perpendicular to the field line. That doesn't look like it. I didn't do a good job drawing this at all. Sorry, I missed it like that. Anyway, and so if I'm going perpendicular to the E field in that path, then you say in that dot product, that looks a little nicer. Anyway, so as I go along that path, right, you say, now it's going to be cosine of 90. That gives me a big 0 here for that dot product. I'm not changing my potential. It's, again, this would be another equipotential line around here at a constant radius out from that charge. And so the point is I end up back where I started physically, right? So if I do a calculation like this, a delta V calculation, but I do it in a path that puts me back where I started again. In other words, if I take an integral over a closed path, so I'm going to put a little circle on my integral sign to mean it's a closed path. You saw me do a calculation like this before. The different formula. You said when we did Gauss's law for electric fields, we did an integral E dot dA is Q in over epsilon naught. But when we did this, I said, hey, I want to do E field dotted with area, and I did it for an area. I had to have a closed surface. My Gaussian surface had to be a closed bubble, and so I did a little loop to signify it was a closed surface that closed on itself. So we caught all those field lines, all the flux coming out. Well, likewise here, I'm doing it over a path that closes on itself, and so there's a little loop there. If you do this, that delta V had better be 0. And you say, well, just logically it makes sense. V is a property of a location. If I go around and I end up back where I started, that delta V had better be 0, maybe back to where I came. In this case, for the path I drew here, the delta V here is the same size as the delta V for this part. These delta V's are 0 in the parts that are going perpendicular to E field lines. You say, but these would perfectly balance each other out. But in fact, any closed path, if I take a spot and I go around and end up back where I started, that delta V for that loop, right, going around, and end up back where I started, that total delta V had better be 0 if I end up where I started. That's the loop law. And that's really just the idea of conservation of energy, right? that if you go ahead and if you have a conservative force, one you can write a potential energy function for, then you remember one of the definitions of a conservative force is that if you look at the work done by that force, so the energy change, right, the work done by the force, and you go around a complete loop and end up back where you started, the energy change for that force is 0. And since delta V is the delta UE per Q, if I make a complete loop, end up where I started, the delta U is 0 because it's a conservative force, the electric force, and so the delta V is going to be 0. So that's it. So that's the idea. So loop law, usually instead of writing it out in the integral form, we usually just write it and we say, hey, delta V for a loop is 0. Okay? But just saying if I go around a complete loop, end up where I started, the change in V is 0. And you say, well, gosh, well, of course, V is a property of location. If I start at this location, it's got a V value. I end up back where I started, I'm at the same V value again. The change has got to be 0. Well, there's a way to get equations, like we got an equation here from the junction law. We can write equations using the loop law and then use those equations to help us solve problems with circuits. And so I want to show you now how to use the loop law. Okay. So to do that, we're going back to this sheet, and I want to talk about this diagram. This is how I'm explaining how to use the loop law. I made that picture in the corner a little bigger so that you can follow it a little bit easier. There we go, or at least I can read it a little easier. So this part is talking about now, here's the formulas we're using. We're using Ohm's law, delta V is IR. We're using the sum of the currents into a junction equals the sum of currents out of a junction. That's Kirchhoff's junction law. And now the loop law, delta V loop is 0. Okay, but I want to show you how to apply the loop law. So what we're going to do is we're going to take a look at different circuits that we're trying to solve, and we're going to make a closed path around the circuit. So, for example, for this diagram, for this sample problem that's on the page, we can make a closed path that goes around the top part. We can make a path that goes around the bottom part. We can make a path that goes around the outside. Each of these paths, we could go either clockwise or counterclockwise around. But the point is, any closed path through the following along the circuit, right, along the conductors in the circuit, any closed path, you can apply that loop law to. And the delta V's had better add up to 0. So how do I calculate the delta V's? How do I write the equation? That's what this bit's about. So what I'm going to be doing is I'm going to be adding up all of my delta V's going around a closed path in the circuit. Add up all the delta V's, and then once I've added up all delta V's, they better add up to 0. So as I go around my path here, I've got to add up a bunch of delta V's, right? Look at the delta V's for this part of the circuit, and then for going through this piece of the circuit, and then delta V for going this piece of the circuit, and delta V, you know what I mean? For each of the different items in the circuit. So here's how we're going to calculate the terms for our equation for each of these different circuit elements. So first, if I have a battery, you, I hope, recall from previous videos, or maybe from your notes from the very start of electric potential, that this symbol, this script capital E, is something that we use sometimes for the voltage of a battery. Okay. In particular, it's like the idealized delta V for the battery, assuming it doesn't have any internal resistance, that internal resistance of the battery is small enough to ignore. This is kind of like that ideal voltage of the battery. It's what you would get if you took an open circuit voltage for your battery. So you had the battery not hooked in, currently operating, and you measured the delta V across the two terminals of the battery. That's what you get. So this is just the delta V of the battery. Now, for these diagrams, it matters when you write your equation, whether you're going clockwise or counterclockwise. It'll affect how you write your terms for your equation. In other words, and so for each element, the direction you're reading the circuit as you go around and make your loop, as you make your path, the direction you go is going to matter, whether you're going up voltage or down voltage, right? Depending on which direction you're going. So say in this one, we're reading, for all these examples I'm going to draw, we're going to read the circuit from left to right. So we're reading along, following along this way. And so for this first one, if I want to go from left to right, here is my battery, okay, with its voltage equal to this EMF symbol, right? EMF is another name for voltage. And so you say, I'm going from, look, the short line to the long line. Isn't that short line the low V side and the long line the high V side of the battery? Yeah. And so I'm going from low V to high V. I'm going up voltage if I'm reading from left to right on this particular battery. And so my delta V is just going to be whatever that EMF of the battery is, however many volts it is, I'm just going to go up. I'm going to add that much. That'll be a term I put in my equation. On the other hand, if I'm reading the circuit from left to right, what if I'm reading this one from left to right? Now I'm going from, see the long line, the short line? I'm going from the long line side, that's the high V side, to the low V side, the short line. I'm going to go from high to low, I'm going down the voltage of the battery. So it's going to be minus the EMF of the battery, is the way that I put that into my equation. Okay, we're going to do a sample problem in just a second, but so we'll come back to this, but this is the way you would do it. On the other hand, now I have to do a battery. I'm sorry, those batteries. Now we're going to do resistors. In the case of the resistors, not only does it matter which way we're reading the circuit, okay, if I read the circuit, am I going left to the right or right to left? It also matters which way the current is flowing in that wire. Matters for this. Doesn't matter for this. For batteries, does matter for resistors, okay? So for this example, we're going to say that, again, we're going to read our circuit from left to right. Okay, so I'm going around, I'm doing my calculation, writing my calculation, going left to right. But in this case, I happen to be going in the same direction as the current is flowing. Okay, so say that current is flowing to the right. I'm going with the hypothetical positive charges flowing this way. I know it's really electrons going the other way, but we're treating it like positives. As my positive charges go through this resistor, as they wiggle through and bump into those atoms, they're dumping off energy, right? So a hypothetical positive charge would have more energy before it goes through the resistor, less energy after, right? Because it dumps off energy in the resistor. So here I'm seeing those charges before they lose energy, and here I'm looking at them after they lost the energy. So my energy per charge is going down for these hypothetical positives. Agreed? So I need to go get a negative answer out for this. I'm going down voltage. All right, the voltage got to go down as I go from before the resistor to after the resistor, going with the way the charges are flowing. Well, how do you calculate the delta V for a resistor? Oh, well, that's what we use Ohm's law for. Delta V is IR. I'm going down, so I'm going to write minus that current times that resistance. So minus IR. That's coming from Ohm's law. That's how I calculate it, putting it into my equation. I'll go minus IR. What about this last case? Well, now, again, I'm going to read the circuit from left to right. We're assuming we're reading left to right here. Now I'm going against the current, aren't I? And so what's happening to my little hypothetical positive charges? They're flowing this way. So as those charges go and they flow through the resistor, they dump off energy. They're losing energy. But I'm reading from here to here. So I'm starting by looking at them after they've lost the energy. And now I'm going to where they are before they lost the energy. So I'm going from having less energy to having more energy per charge. So I'm going up voltage. Okay, going up voltage as I go this way. So I want to do plus IR. Okay, so that's how we're going to calculate it for resistors. Now, this is where I like to add a couple things that aren't on that sheet. And so what I want to add is two more cases. Okay, so we did the battery, we did the resistor. Now let's talk about capacitors. So we're going to add in an example with a capacitor. Okay, capacitor, two lines of equal length. Let's say this has a capacitance big C. Okay. Now, if I have a charged capacitor, there is going to be a delta V from one side to the other, right? One of those sides of the capacitor will charge up positively, and one of those sides of the capacitor will charge up negatively, right? So let's just say that this is the side that's got positive charges on it. This is the side that's got negative charges on it, right? And those two charged capacitor plates. And let's say this time we'll do this side being the negative side, the low V side, and this being the positively charged side, the high V side. Okay. So you will agree that if I have a charge, if the capacitor has had time and it's all charged up, there is no current flowing here, right? It's not jumping the gap, right? So there's no current, so it doesn't really matter what way current's trying to flow in the circuit. But what matters is just I'm going from high V to low V. If I'm reading left to right here, aren't I? If I'm reading the circuit going this way, whoops, then I am going from the high V side to the low V side, so I need to go down voltage. You say, and if I'm doing this one, going from left to right, I need to go up voltage. Okay, great. So I understand what the sign has to be. How do I calculate the voltage for a capacitor again? This is where we're going to use the formula, and I'll go ahead and throw this up here at the top. We're also going to be, for capacitors, we use the formula. Don't you remember a capacitance is the Q per delta V across the capacitor plates? We're trying to find the delta V across the capacitor plates. So I'll just rearrange this and I'll say delta V equals Q over C, the Q on the plates divided by the capacitance. So if I rearrange this guy, for this one, I'm going down capacitance from the high V to the low V. So my delta V is going to be minus Q over C. All right. Now, we're going to talk about the very last stuff we'll do in this unit is going to be looking at while the capacitor is changing the amount of charge on the plates. And so then I'll usually make the Q a lowercase q. So it's like a variable. It can be changing as it charges or as it discharges. Okay. But it'll be minus Q over C if I'm going from the high V to low V side. If I'm going from low V to the high V side, I'm going to go up Q over C. And that's how I calculate my delta V's for a charged capacitor. So these are the different ways that we can handle these different circuit elements in a circuit. This is the way we'll put them into the loop law. Let's do an example so you can see what I mean by putting them into the loop law. Okay. Now, this page in your packet has a specific example here, and it kind of runs through a solution here. And it kind of talks through it as it goes, which is very nice. This is from the old textbook we used to have for this course years ago. And I kind of ripped this example off. I'm going to go ahead and work their example. Okay, and I may work it a slightly different way than they do because I want to talk about it a little bit more. So let me draw this over a little bigger. Oh, look. And we'll kind of talk through it here. So here is the circuit we're setting up. This is a problem that you would be hard-pressed to solve using the techniques without the junction and loop laws that we've just learned. Okay, you would have a rough time trying to solve this one, I think. All right, but with junction loop laws, we can set up some equations and solve it, no sweat. So, taking a look at this, first we're going to start by writing some loop laws. Okay, is what we would do. But before I dive into this, right, junction laws say, hey, I want to look at all the currents going in equals all the currents going out, right? So I want to use the junction law in this setup. So the first thing I want to point out is how many different currents do we have for this circuit? Wouldn't you agree that however much current is flowing in this part of the wire here, doesn't that have to be the same amount of current as is flowing in this wire here? Because they're connected up like this, right? And there's nowhere else for the current to go. There's no junctions. And so whatever's flowing in here has to be the same as what's flowing in here, right? Don't you think? If this is flowing up here, it's better be flowing to the right here, better be flowing down here, yeah? If it's going up here, it better be going left here, better be going down here, right? So there's whatever the current is here, 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 it's got to be the same current in all of those parts of the circuit. So, but once I get to a junction here, that current could split up, right? And so I might have a different amount of current flowing this way and this way, right? So there's some amount of current that flows to the middle here. What about here? Whatever flows in this part had better be the same as what's flowing in here and flowing in here because there's no other choices for it to go, right? So that's to say that in this circuit, there are 3 different currents. Okay, I can potentially have 3 different currents. One in the top part, one through this middle branch, and one through the bottom branch, right? So I'm going to give them names. I'm going to give them variable names. Okay, we'll call them I1, I2, and I3. Now I'm going to go ahead and I'm going to follow what the sample problem here with their naming convention, okay, regardless of whether it's correct or incorrect. I'm going to go ahead and use their naming convention. Now what we're going to do is we're just going to give them some names, I1, I2, and I3, and we're just going to guess what way the current is flowing for now. In the end, it'll all work out okay, and we'll figure out what the currents are and which way they're really going, and that's fine. But for right now, for setting up the equations, you can just guess. And so they guessed. They said, what's going in this middle branch? They said, let's call that I1, and let's just guess it's going to the right. We'll call what's going in the top part here. We'll call this I2, and we'll guess that it's going clockwise. And then the bottom branch, they said, let's call it I3, and let's guess that it's going clockwise. So if I call this I3, that's the same as what's flowing in this and same as what's flowing in this. If I call this I2, that's the same as what's flowing. All of this is I2. All right. Now, the directions they chose here, I'm just saying, they're not correct. Okay, they're not all correct, and that's okay. We'll see in the end which ones have the directions wrong. You'll be able to tell from the answer. It'll be obvious. So here, we'll set up using their notation. So we want to do junction law. So what I'm going to do is, when I write junction law, I'm just going to look at a junction. Now, how many junctions are there? Places where the wires are splitting or coming together? There's two in this circuit, aren't there? There's a junction on the left here, and there's a junction on the right over here, right? So I'm going to go ahead, I'm going to write the junction equation here for the right junction, and then I'll write it for the left junction so you can see them and see how they turn out. For the right junction, what would I get? Again, we're going to do the sum of all the currents going into the junction equals the sum of all the currents going out of the junction. So what's going in towards this junction? Into is like towards it. Well, I1 is going towards it, and I2 is going towards it. But I3 is flowing away from it, out of it. So this is going to be I1 plus I2 equals I3 is the equation we would get. Let's take a look at the left junction here. What if I wrote the equation for the left junction? If I had done that, we want to say current's going in towards it. Well, what's heading towards that? I3 flows around and goes into that junction, doesn't it? So I'd have I3. But I1 is clearly going away, right? It's going to the right. It's going away from that junction. So that's going to be one of the currents going out. And I2, it goes around like this, yeah? So I2 is going away out of that junction. So it's on the outside of the equation. So that's the equation I would get for the left junction. Now, something that you might spot right away about this is you say, wait a minute, compare these two equations. They're really just the same equation with the sides flip-flopped, aren't they? You can rearrange this to be this, right? So these are not two independent equations. Do you remember solving systems of equations? That's what we're going to do. And you have to have independent equations to solve. This is just a repeat of itself. It's not helpful to have both of them. When you do junction laws, when you're solving a problem, you generally are going to do one less junction law than you have junctions. Okay, is the general rule that works. So like if I had another branch going across here with like some resistors in it or something, then I'd have another, I'd have another current to deal with. Actually, I'd add a bunch of currents, right? If I branch this, then what's here might be different than here. And okay, that's for another time. Let's just say you don't use every possible junction because you would end up repeating yourself. You'd get equations that are just repeats rearranged. So typically you're going to do, I think that it ends up just being, if you've got n junctions, there's going to be n minus 1 junction laws you can write. I believe. I got to think about that. But you get the idea. Okay, now let's do loop laws. Okay, in loop law, that's the one where we say my delta V's, and what this really is, it's adding up all of your delta V's going around, delta V for each circuit element, going around in a closed loop. Your delta V's better add up to 0. Okay, so it's almost like there ought to be a sigma in front of this, but I guess it looks weird having a sigma delta. I'm adding all the differences. I'm taking the sum of the differences. Anyway, so if I take a look at this, we're going to do some complete closed loops. And you say, well, how do I do a closed loop? You say, well, we could do a loop around the top part. We could do a loop following the current going around the bottom part, or we could do a loop around the outside. Each of those we could go clockwise or counterclockwise for. So there's like 6 different ways. But you will see that if I go around a path clockwise, and if I go around that same path counterclockwise, the equations will be identical with just all the signs flipped, which is just the same equation, really. Just multiply through all the terms by -1 gives you an equivalent equation, not a new independent equation. So let's go ahead and write some loop laws. So let's go ahead and choose, for our first one, let's do, we'll write all 3. Let's do the top loop. Now, when I do a loop law, I can choose anywhere on this, say I want to do the top loop here. I can choose to go clockwise or counterclockwise, doesn't matter. The equation will look a little different, but it'll be equivalent. I got to pick a spot to start on the loop. and then go around in a circle and end up back where I started so that I have a closed loop. My recommendation for you, what I typically like to do whenever I solve these, is I usually start by going to the biggest battery, the highest voltage battery, which would be this one. And I like to start at the low V side of the battery and then go through some going up voltage. So that makes that really big delta V a nice positive big number. It makes it a little easier in doing the math. So I'm going to do this, and I'm going to go around the circuit. I'm choosing to go this way, this way, this way, end up back where I started. Make sense? So I'm reading the circuit going this way. Okay, and it doesn't matter if that's the way the current's going or not, but that's the way I'm gonna draw my loop. So here we go. Let's start with this. If I start at the low V side of the battery and I go up, I'm going from the low V side to the high V side, so I'm going up the voltage of the battery, right? That's what our rule is. If I have a battery and I go from the low V to the high V, I'm going up the EMF of the battery. So that's what we're going to do. So I'm going to go up 14 volts. Okay, this is the top loop is what we're doing. And for what it's worth, we're going counterclockwise. Okay, so I'm going up 14 volts. Now what happens? Well, now I'm going to go through the 4 ohm resistor. And you say, now, we said that I2 is flowing clockwise, but we're going counterclockwise, reading the circuit. So if the current is flowing this way, then as it goes through the 4 ohm resistor, these charges would dump off energy, and then they'd have less energy on this side. We're reading this. We're going from after they lost energy to before they lost the energy, to when they had more. We're going to go up voltage. Okay, we're going to go up voltage as we go this way. So I'm going to add plus IR, right? But you say, when I look at that, you say, we're going to go up IR because we're going after they lost the energy to before they lost the energy. You say this I is actually I2, and the resistance here is 4 ohms. So a lot of people like to put the 4 in front, the resistance in front, so it's like a coefficient, it's just like up 4 I2. That's all right. So we're going up IR. Now what are we doing? Now we're going through this middle branch, right? And we're continuing in our loop. Now we're going to go, look, we're going to go from the low V side, short line, to the high V side of that battery. So we're going to go up 10 volts. Now we're going through this resistor. This time, we're going the same direction as the current is flowing, the way that we assigned current. We said I1's going to the right, we're going to the right, we're going with the charges. As they go through resistor, they dump off energy. So we're going from before they lost the energy to after they lost the energy. So we're going to be going down voltage, right? So we're going to go down the current. This time, it's I1 is the current in this branch, and our resistance is 6. So we're going to go down 6I1. And now I'm going to continue on. I'm following along here. Finish my loop, comes back to where I started. And that's it. I didn't run into anything else putting energy into the charges or taking energy out of the charges. So I am back to my starting point. So all these ups and downs going up voltage, down voltage, up, down, those better add up to be 0. And that's how I write a loop law equation. Okay, so here's an example of running around, adding up all my delta V's. And when I end up back to my starting point, all those delta V's had better add up to 0. And so I've got an equation here that has 2 unknowns, I1 and I2. Perhaps I can combine that equation with some other ones and solve those simultaneous equations and get the values for all my currents. That's the plan. Okay, but this isn't enough. I need some more equations. How many unknowns do we have here? Well, in this problem, they gave us all the voltages of the batteries, and they gave us all the resistance of the resistors, but they didn't give us any of the 3 currents. So we've got 3 unknowns. And something you know is if you got 3 unknowns, you need 3 independent equations to solve for those 3 unknowns, typically, right? That's the way it works. These are not 2 independent equations, right? It's just the same equation, rearranged. So I only have 2 equations. I'm going to need at least 1 more loop law. Okay, we usually end up with more loop laws than we have junction laws. Okay, when you write your equations, you'll have more loop laws than junction laws. So let's do another loop. Would you like to do, let's do the bottom loop. Okay, let's see, let's pick another color. Maybe we'll do this one in purple. So I want to take a look at this bottom loop, all right? How shall I go? Well, I like to start at the low V side of my biggest battery and then go through that battery. So I'm going up voltage at the start and loop around. So I'm going to choose to start here for my purple loop, and I'm going to go okay, and end up back where I started. So we're going to do the bottom loop. Okay, we're going to do this one clockwise. Okay, so first thing I'm doing, I'm starting here. I'm going to go up 10 volts. I'm going from the low V to the high V side of the battery. So I'm going up voltage, up 10 volts. Now I'm going to go with I1 through that 6 ohm resistor. If I go with the current, I'm going to go down voltage, right? Because I'm going from before the charges went through the resistor to after they've gone through, after they've dumped off energy. So we're going to go down IR. This is going to be down I1 times 6. And I come along here, and I come along here. Here we go to this resistor. Now I'm going with the current, aren't I? I3 we labeled to go this way. We're going with I3. And so with the moving with the charges, we're going from before they lost the energy to after the charges flowed through and lost energy. So we're going to go down again. Now it's going to be down I3 times 2, because this is I3 is the current in this branch. If I continue following along, it gets me back to my starting point. So my delta V's had better add up to 0. I'm back to the start. Okay, this is enough to actually solve this problem, but for sake of completeness, I'm going to write one more loop law for you. And you say, hey, what if we did the loop around the whole outside of the circuit? Okay, I guess I'm going to do this one in, I don't know, is that teal? Aqua? I don't know, I can do it in teal. So I'm going to go ahead, let's pick a spot to start. Well, we're going to go around the whole outside, one way or the other way. Again, I like to choose the biggest battery, so I'm going to choose here, I'm going to start here. And I'm going to go around through the battery from low V to high V. So I'm going to start the low V side of the biggest battery. Here we go, and go through the battery. Going this way. Going this way, right? Going this way, right? Going this way. And end up back where I started. So let's write that loop. This is the, I don't know, outside loop. And it looks like I'm going counterclockwise. So starting here, I'm going from low V to the high V side, so I'm going up 14 volts. Now am I going with or against the current here? We said I2 would be going around this way. So I'm going against the current, so I'm going to go up. So I'm going from after they lost the energy to before the charges lost the energy. So I'm going up. IR, I2 times 4. Now I'm going around, there's nothing here. Oh, there's a resistor. I'm going with or against. Well, look, we said I3, we said we'll be going this way. We're going against it. So we're coming after the charges went through the resistor and lost energy to before that current went into the resistor and lost energy. So we're going up I3 times 2. Nothing else to run into. We're back to the starting point. That had better add up to 0. Now, it's not so easy to see just glancing at this, but these 3 equations are not 3 independent equations. If you tried to solve just using loop laws, you would find that stuff would like cancel out and drop out, and you wouldn't get enough information to solve, okay? Because these are not 3 independent. They're kind of like this outside loop is kind of made up of the other 2. Actually, can you tell that from looking at this? Nope, not really. Okay, but believe me, this is really just made up from the other 2 equations. And if you tried using just these 3, it would not work. It would crash on you. Yeah, I could show that. Like, for example, I don't know, maybe should I try to show that? This is probably something to show you after we've solved the right way, right? I'm going to do it now anyway. Let's say that we tried to solve using just these 3. Let's take the top one, right? So if I take that top loop, there's a bunch of different ways of solving simultaneous linear equations. I'm going to rewrite this with like coefficients. 4i2 plus 10 minus 6i1 equals 0, right? And my favorite way is to solve by substitution. But you can like do that whole thing where you like add or subtract equations from each other too to help simplify, and that's fine. Here's the outside loop. 14 plus 4i2 plus 2i3 equals 0. If I did these, you might look at these and say, oh, wait a minute, why don't, if I subtract the teal equation from the orange equation, so if I did this minus this, you know what I mean? Look what's going to happen. Right? And so I'd end up with 10 right, minus 6i1 minus, because I'm subtracting, minus 2i3 equals 0 is what I would get. And you say, so I eliminated one variable, eliminated I2, and now I go to, say, this bottom loop equation, right? That'd be 10 minus 6i1, right? So I've got what? 10 minus 6i1 minus 2i3. You say, you tell me, what happens if I now subtract this equation from this one? What do I get? Chunk, 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 chunk. Everything drops out, right? And you got nothing solved. See? And you get the big, 0 equals 0. That's not helpful. Okay, so we really absolutely need to do a combination of junction laws and loop laws to solve. Okay, we cannot solve this just using junction laws or just using loops. It's not enough. Okay, we got 3 unknowns, we need 3 equations, we have to do a mix. So let's go ahead and let's pick 3 equations to solve. Okay, we're not going to use both of these because this is, again, this is just the other one rearranged. We can't use just these 3 because we just saw what happens. Everything ends up canceling out. So we're going to pick 2 of the loops and 1 of the junctions in this case. Okay, so you're always going to have more loop laws than junction laws when you solve. Okay, you're never going to use all the junctions. Okay, so let's set this up. I'm going to take these. I'm going to solve them. Am I really going to try to squeeze it into this tiny little space? Would I do that? I am crazy enough to try to do that, but no. I'll be a little nicer with it. I'll give myself a little room. Okay, so let's go ahead and give this a shot. Okay, we're going to go ahead and use this, use the junction law. Let's go ahead and use we'll use the right one. That's kind of nice. I1 plus I2 equals I3. So we're going to use that equation. Do you want to just use the top loop and the bottom loop? Sounds good. Okay, so let's use those. So what I might do is I like to solve by substitution. Okay, I don't know why I'm rewriting these like this. This seems, I know why. I really like to have the coefficients like that in kind of that coefficient format. So I got my 3 variables, I1, I2, I3, 3 equations. Let's solve simultaneous equations. Let's solve. Here we go. So I like to eliminate variables. That's the way I like to do it. I generally don't do like the adding and subtracting of equations things unless I happen to see 2 terms that'll just drop out nicely as it is. So what I might do is I might first say, let's get rid of I1. Sound good? So I'll take an equation. Look, here's one that has just I1 and I3 in it. That's actually going to be really nice, only having 2 variables in an equation. And so if I rearrange this, I might get that I1 is equal to, let's see here, move this over, right? I'll have 2i3 divided by 10, right? So I'll have 2i3, right? And then I'll have minus 10, and then I'm going to divide through by that negative 6, okay? That's what I1 would be. Do you want to make it pretty? Yeah, I want to make it pretty. So this will be, what's 10/6 anyway? That's 5/3, right? So that'll be 5/3 minus 1/3 I3. Okay, so that is what I1 is equal to. So I could take this, and I could substitute that in wherever I see I1 in the other 2 equations, right? Okay, so let's go ahead and substitute that. I'm going to substitute that into the, well, I guess I'd be doing it in both of them. So if I go ahead and do that, this could get plugged into where it says I1 there, and I'll also substitute in to where it says I1 there. I have this nagging feeling in the back of my head like there's a quicker and easier way of doing this example than the way I am, but what are you going to do? So that top equation is now going to become 5/3 minus 1/3 I3, okay, plus I2 equals I3. And so I have an equation that just has I2s and I3s in it. And you say, okay, that's nice. We got rid of the I1. And you say, in the second one, this orange one becomes 14. Can I add that 10 to the 14 right away, make that a 24? Okay, plus 4i2. If I move that 6i1 to the other side, that would be equal to 6 times I1, which is this black bit. So I move that to the other side. So that's going to be what? 5/3 minus 1/3 I3. Okay. And you say, okay, so I've got another equation that has just I2s and I3s in it, right? And here's I3s and I2s. So I got two equations, two unknowns now. I had three equations, three unknowns. Now I'm down to two with two unknowns. And you say, we can go ahead and get rid of a variable. Let's get rid of I2. Why don't we solve for I2? This top equation, what's I2 going to be equal to? You say, well, let's move this junk to the other side. And so I'll have, here's an I3, and I'm going to add an I3, so it'll be 4/3 I3. And then I'm going to add this this 4/5. I'm going to subtract over the other side, minus 5/3. So that is what I2 is equal to. So now I could take this, and I can put it into this equation where it says I2. And if I do that, there's going to be 24 plus 4 times that bit I'm subbing in. Right? On the right side, I've got that that's equal to 6 times 5/3 minus 1/3 I3. And say, now I just have one unknown, I3. It appears in two spots. I'm going to group my like, I'm going to go ahead, distribute, group my like terms, rearrange, and solve for I3. So if I do all of that, gosh, annoying math, if I do that, let's see, let's do, I'm going to handle this part. So let's see, we're going to have 24. This is going to be plus 16/3 I3 minus 20/3 equals, on the other side, I'm just distributing here, 30/3, oh, that's going to come out nice, minus, 6/3, that's just minus 2 I3. Is that okay? And 30/3, that's just 10. Okay. All right. I don't know why about it. I'm going to have to combine thirds in a minute anyway. Okay, so now I have that. Let's move this 2i3 to the other side. So if I made it into thirds, this would be 6/3. I'm going to add that to 16/3, and that would be 22/3 I3. Let me put all the constant terms to the right side. And so that's going to be equal to 10, and I'm going to add 20/3. I'm going to subtract 24, right? Yeah. You know what 10 minus 24 is? Negative 14. Negative 14 plus 20/3. Simple math, I know. If you do that, that's going to be 42/3. So it's going to be 20/3 minus 42/3 is negative 22/3. Okay, so what I have now is, and you say, oh my gosh, look, 22/3 I3 equals negative 22/3. Holy cow, you know what I3 is? You say, yeah, I3 is negative 1. Okay, is what that came out to be. So it's negative 1 amp. Okay, now I know what I3 is. I can go back to my other equation. Like, see this one? Here's an equation for I2 with just one variable, I3, in it. So I just put that negative 1 in there, and you say, and when I do that, you say, holy cow, I'm going to be able to get what that is right away. I'm going to get that I2 is 4/3 times negative 1. That's a minus 4/3 minus 5/3. That's going to be a minus 9/3. You know what minus 9/3 is? That's just going to be minus 3 amps is I2. And now I can go to an equation. Look, here's an equation I wrote for I1 that only has one variable in it, I3. And I3, we figured out was negative 1 amps. So you say, hey, what's I1 going to be? You say, if I go ahead and I use that, you say I1 is going to be 5/3 minus 1/3 times negative 1. That's going to be plus 1/3. 5/3 plus 1/3, that's going to be 6/3. And 6/3 is just going to be 2 amps. And so I1 is 2 amps, I2 is negative 3 amps, I3 is negative 1 amps. And I know you're thinking to yourself, wait. What's with these negative signs I'm getting? Do you know what those negative signs mean? These are the correct magnitude currents. The negatives mean that when we assign directions back at the start here, we got them flipped. We got them backwards. So what's really happening here, right? I1 is 2 amps. That is flowing to the right because we got a positive 2, right, for this. So what's really happening is we've got 2 amps flowing to the right here. When it gets to this junction, it splits. And these directions are backwards from what they should be. I really should have flowing up this way. I2 came out to be negative 3 amps. So it's really 3 amps going this way. And I3 calculated out to be minus 1 amp, right? And so minus 1 amp means it's really going this way, 1 amp. Now look at this. 2 amps flows in this way to this junction. 1 amp flows this way. 2 and 1 come in together. They're 3. 3 comes along, gets to here, splits up. 1 amp goes this way. Or sorry, 2 amps goes this way, and 1 amp goes this way, right? So 3 comes in, splits up, comes together. 3 amps goes through, splits up, comes together. That's what's happening in this circuit. All right, and that's so it's okay when you first just assign your directions for currents. You can kind of choose whatever you want, right? And if you happen to assign the direction incorrectly, you're just going to get a negative out at the end. Your current will calculate out to be negative, and that's okay. That just tells you got the direction flipped, and that's okay. And you still get the correct answer at the end. You're just like, oh, I fixed the direction. It's going the other way, and it's this big. So that's it. So that's an example of using Kirchhoff's laws, junction law and loop law, to solve a circuit problem. With multiple batteries or with capacitors, you don't have a choice. You're going to need to use Kirchhoff's laws to solve. Okay, you can't just use delta V's IR by itself. Okay, you're going to use them together. One more thing about this, just as a side note, I don't like to have my directions assigned incorrectly at the start. I find it annoying. Okay, to have to go back and get these negatives, have to flip things and think about my head differently than how I did before. So my tips for figuring out which way the current is really going to flow, here's what you do. Remember, the batteries you can think of as being almost like pumps pumping water. They're pushing charges from high V to low V. So I can imagine then my current, the biggest battery, typically it's going to win. It's going to get to push the current the way it wants to, right? And so typically I'll start at the highest battery and I'll say, okay, we're probably going to push current that way, right? And it's going to come here, and when it gets to here, it's going to split. Now, it could all flow down and some more could join it from this way. But you see this branch? I've got a battery shoving this way. There's no other battery pushing in this branch. This battery wants to push the current that way. So I think that it's probably going to win, and we're going to get the current flowing this way in that branch. Now, this comes in, this comes out. What about this bottom bit? Could it get pushed around this way, or could it get pushed around this way? Well, if I think about it like that, this 14 volt kind of wants to shove out away from itself, right? And this 10 volt wants to push the other way. The 14 volt's a bigger one. I think it's going to win. We're going to go around this way. But yeah, I agree. It wouldn't be necessarily so clear to me at the start that what's really happening is it's coming out here, it's splitting, going out, coming back in. Coming along here, splitting, joining back up, coming back in. This is the way it's flowing because this battery is pushing it that way. Okay, and so I can kind of logic through sometimes at the start so that I make sure I get my currents going the right direction. Again, not a big deal if you assign a direction the wrong way. You'll know at the end of the problem when you get negatives on your currents that, oh, the direction was just the other way. But the magnitudes are right. They really are 3 amps and 1 amp just going the other way. Okay, so what's next? What's next is going to be going through some of those other Kirchhoff's law problems that are in the packet on the next page. There's like 5 problems. I provided solutions to 3 of them. I need to double check and make sure there aren't some errors in those. I have a feeling that there are. I didn't show solutions to problem 2 and problem 3 because there's some special things about them I want to talk about for sure. Okay, and one of them is really weird, and I didn't want you to get frustrated by it. I'd rather talk through what happens and why.